Norway. Energy so clean, you can drink it. And that's why I'm here, to look at the most successful energy transition in the world. My name is Scott Tinker, and I study energy. And I was headed to the Stavanger hydro plant.
So the easiest access to the power plant was to tunnel through the mountain?
Yes, I guess not the easiest, but the best altogether, yeah.
The tunnel is how long?
1,500 meters long.
How far under the mountain are we now?
We are 500 meters.
When the tunnel stopped, I realized we weren't going through the mountain. The power plant is inside the mountain.
There's nobody here.
No, there normally is nobody here. All our stations are run from our central in Bergen.
Wow. I'm very curious about this. What's on the wall here?
It's a piece of art, a waterfall with a salmon on the right here jumping up the waterfall.
So there's art down here in this plant.
Yes.
That's beautiful. It looks like the end of a cathedral.
Yeah.
And this is an interesting design. I mean, what is that?
So this is constructed to transform the energy of the water into rotating energy in the wheel. It was an American gold digger digging gold which discovered that he could use the energy in the water much more efficient if you had a cup form. So you get to use over 90% of the energy in the water. What you see is the top of that generator.
What are the rotations?
500 revolutions per minute.
500 RPM.
Yeah. There's 200 tons rotating.
These generators are connected to lakes in the mountains high above us by a 20-mile underground pipeline network. No huge dams, and the environmental footprint is tiny. With technology like this, Norway now gets 99% of its power from water. Lots and lots of water.
So it's cooking by the time it gets here.
Oh, wow.
How fast? 5,000 gallons a minute?
Yes,
Yeah.
between 4,000 and 5,000 gallons
gallons
per second.
Per second.
It took Norway 70 years to turn this nearly perfect energy source into a nearly perfect electricity system. And what I'm trying to find out is what will the energy transition look like for the rest of us? And how long will it really take to make the switch? By training, I'm a geologist. I run the Bureau of Economic Geology.
Critter.
You can even pick out the trail when you get up here and look pretty close. There's a lot of...
I'm also a professor at the University of Texas. Being in the field is the best part of being a geologist.
This black is actually a hydrogen to carbon ratio.
I speak around the world, to governments and industry and at universities, trying to build a common understanding of energy. That's my passion.
And the bottom are actual units in quad.
But my background is mostly technical. I realized that if I was going to figure out our energy transition, I had to experience it. I needed to see how energy is made, from coal to solar and everything in between. It was time to get out of the lab and back into the field. While I was packing for my trip, I had an idea. I decided to add up all the energy that goes into everything in my life. Like all the clothes. Most of them are made in a factory, then shipped around the world to my closet. Then I ship them around with me. That's a lot of energy. Add to that the energy to run and to make the dozens of gadgets that I use every day. Then add the energy to build and power everything in our house. The appliances, furniture, the house itself, everything. Add on the energy to run my car and to build my share of the roads. And to heat and cool my share of every building I go into, like the airport. If you add up the total energy that one person uses in a year, it comes to a gigantic number. 20 million watt hours. But the energy unit I would use is me, or you. One person's total energy footprint in a year. And as I travel the world looking at electricity and transportation, that's how I'll measure every energy source I visit, by the number of people it would power in a year. The first thing I needed to understand is what we're transitioning from. And for electricity, that's coal. To get a better look, I went to the Bel Air mine, which makes enough energy to power 3.6 million people per year. It's in the Powder River Basin, the largest coal reserve in the world.
Fire on 24.
We will clear the blast momentarily, and we're safe to mine.
Is that right?
In minutes.
Wow.
There's the coal inventory right there.
That is a big pit.
The Powder River Basin has a typical coal seam of about 100 foot thick. So,
I mean, it's this big, thick black seam down here. It's unbelievable.
the mine, it looks enormous, but the mine moves actually quite a bit. We will move about 3,000 feet a year across the landscape.
Okay.
Okay? So these big terraces are excavated on the cut side, we call it, placed back on the dump side. This will all be reclaimed, and the original topsoil that was taken from this area will be placed right back directly where it was taken originally.
It's kind of hard for me to get a feeling for scale. I mean, I see little trucks driving around out here. They look like the little Tonkas I used to play with.
That is the largest mining truck in the world, Scott. That's the Caterpillar 797.
Okay.
That's a 400-ton payload truck. This particular machine is the largest rope shovel in the world.
And the price tag?
It's about $30 million.
30 million bucks.
With the bucket and all the accessories.
Take care of it. Wow. This is amazing. That's a lot of material.
Put it in perspective, the volume of material we dig annually would be 3 Panama canals.
Every year.
Every year.
The whole Panama Canal?
The entire Panama Canal.
Many people think it's that dirty black stuff,
Yeah.
but in fact it's been powering a good fraction of society for a couple hundred years. So there must be some upside, right? Coal supplies about half of the electricity generation in the U.S. and globally is also about half, maybe a bit more, of the primary energy. So the world gets a lot of its energy from coal right now.
And there's a lot of coal left.
There is a lot of coal left, hundreds of years.
Yeah.
In fact, nobody really knows because nobody's gone exploring for coal for many decades.
Every day we ship approximately 80,000 tons of coal. That coal that you see right here was probably mined 4 to 6 hours ago.
And how often do you move a train through here?
We do 5 trains a day.
Wow. So it's just a steady flow.
Steady flow of trains, 24 hours a day, 7 days a week, 365 days a year. We ship coal on Christmas, Christmas Eve, New Year's Eve.
Somebody's always
getting coal.
How much coal are we looking at in the Powder River Basin?
There's literally billions of tons of reserves.
Give me a feel for what that means in terms of just U.S. supply.
Powder River Basin represents 50% of that.
So make sure I understand. About half of our electricity comes from coal.
Correct.
And about half of that is coming from the Powder?
And half of that is coming from right here, this quiet little community in northeastern Wyoming.
Who knew that?
I think very little people do know that.
So coal is global and easy to produce. Is supply the only reason we're still hooked? I followed the trains to America's largest coal plant, which could power 900,000 people per year.
All these cars have got a rotary coupling on them, so the cars will spin on the coupling.
Okay.
And you watch what's going to happen. These clamps are going to clamp down on top of the car. Then this whole dumper is going to turn upside down.
Track and all?
Track and all.
Trains are running
Around the clock.
Yeah.
Trains running around the clock, unloading coal around the clock, moving it to the units, making electricity 24 hours a day.
So this is awful big.
Well, we've got coal coming from the coal yard out there going through this conveyor. That coal is going into each corner of the boiler, makes a big fire in the boiler, heats up water inside the boiler, heats up the steam, steam turns the turbine, turbine turns the generator, generator makes electricity for Texas.
Take a massive global fuel supply, combine it with fast, simple power generation, and you get the cheapest electricity in the world. That's why we're still hooked.
So the big driver really in many ways is the economics.
As in almost all things energy, economics really runs the whole show. On the other hand, coal has these external problems with it, local air pollution, sulfur in particular, and then the global problem of carbon dioxide emissions.
Right.
If the world is going to continue to use a lot of coal and do it in an environmentally responsible way to protect the climate system, then we're going to have to develop and deploy the carbon capture and storage technology that's now really in demonstration around the world.
We've got a project we're working on in the Department of Energy to remove carbon dioxide out of our flue gas. We're going to prove that it can work on a coal unit. We're going to try to prove that it's economical to scale up so we can do a full-scale unit.
Okay.
And then we can actually capture the carbon and put it to good use.
Gotcha. So you're going to have another module, if you will, to remove the CO2 from that stream before it goes into the stack.
That's right.
I went to see NRG Energy, who owns the Parrish plant, to find out if we could really clean up coal.
The trace, that's the real-time desk with the 10 screens.
I noticed the board had all your competitors.
Yeah. You've got, on one hand, the coal industry saying what they're doing now is clean coal, and I think that violates the truth in advertising. I actually think it's really unfortunate that they spend a lot of advertising dollars pretending that what they're doing now is clean coal. On the other hand, you've got the environmental movement saying that it's an oxymoron. There's no such thing. I think that there actually is clean coal, and clean coal it should be defined by the carbon emissions. And if you can get the carbon emissions from a coal plant down below the carbon emissions from a gas plant, so more than 50% down, then to me, you fit the definition of clean coal.
Right.
Our company got an award to do a project down in Texas.
That's at Parrish?
That's at Parrish. We have a grant from the Department of Energy, around $140 million, and we have to match that, so it'll be about a $300 million investment. So you see the type of money we're talking about in terms of learning how to capture carbon. These are very significant dollars.
Sure.
$300 million to to get just 2% of the CO2 at this one plant. Even as the technology improves, that means capturing half the carbon from the world's fleet of coal plants would cost trillions of dollars. We probably could make coal clean, but we probably can't afford to. Coal may be the foundation of our electricity system, but oil is what allows us to move. And what most people want to know about it is price. Will oil and the fuels made from it get too expensive? So I went to the New York Mercantile Exchange, where every day these traders are locked in the high-stakes poker of setting the price of oil.
These are where the 10s are, and these are where the 1s are. So if I want to buy, I always go like that.
Yeah.
If I want to sell, I always go like that.
Okay.
If I want to buy 25, I buy 25. The supply and demand components really all come together here on the floor. All of what you're hearing in the geopolitical arenas, all of what you're hearing in the demand side of gasoline and the supply side of perhaps rigs shutting down or more rigs coming online, all of that information gets really condensed into a settlement price at the end of the day.
Okay.
And that is what people use as a benchmark to set the price from crude oil to gasoline to heating oil to natural gas.
So everything that influences that supply and demand, it could be a storm.
It could very well be a
fire.
storm.
It could be a...
It could be a catastrophe like an earthquake.
Right. What impact does oil price have on the overall economy?
It, to me, has the biggest impact of any commodity there is, and that's why it's of such global importance, political importance, and down to the nuts and bolts, guy in the car, guy in the truck importance.
Oil and the economy are intertwined. In fact, 6 of the last 7 global recessions were preceded by a spike in the price of oil. And that is driven fundamentally by supply and demand. So where will future oil supply come from? Offshore is the fastest growing production area, so I decided to go see Perdido, the deepest water platform in the world.
Starting one.
Perdido is a very long flight for a helicopter, so everyone going out first has to do Hewitt, helicopter, underwater, escape training.
And step off. Squeeze in tight, make it hurt.
They reassured me if my helicopter crashed, I wouldn't need any of this, because I probably wouldn't survive. But if you do an emergency landing on the water and then sink, Hewitt teaches you how to get out.
Everybody ready?
Yeah.
Ready inside. Stand by for engine. Brace for impact. Brace, brace, brace.
Hewitt was a reminder we're headed into a remote and dangerous environment. The Perdido platform is more than 2 hours from shore by helicopter and could power 1.7 million people per year.
Chris, where are we? So right now we're 200 miles south of Galveston. We're on what's called a spar, and a spar is basically a can, a floating can if you want to think about it. So the can's held down by a
big weight.
Okay.
And it's like a buoy. It's just floating there.
So this is the deepest water platform
Deepest water
in the world.
We're at 8,000 feet of water.
8,000 feet.
And we're producing, and we have the rig on board so we can work on the wells as well. The spar rig, which is straight above us, has access to 22 wells directly beneath the spar.
How long did it take to get this facility in place? I mean, from the first time you guys decided, hey, some geologist like me says, we're gonna drill here.
First of all, we have to decide you're right. From the time we purchased the lease to the time we got first production in March, it's 14 years.
14 years. What's this cost?
You know, several billion dollars.
Several billion dollars.
Yeah. So this is the brains of it. This is the control room. This is where we'd control the movement of the spar.
Gotcha.
So we actually have one of our engineers in New Orleans that we're connected to. So if we have a problem, we can actually use people from onshore to help support us.
That seems like a pretty critical and important function then.
As the platforms we're getting to are more and more remote, I think it's more critical. It's tough to get help out here if you needed it.
I mean, fresh on the minds of people, of course, is the Deepwater Horizon accident. Describe for us how you see that incident and what Shell's been doing to make sure that those kinds of things don't happen.
I think it taught us all a lesson. And what we've seen now is a group of companies basically create the tools needed. So we have the subsea equipment ready to respond to a blowout event.
Okay.
Other than that, I think we can use remote monitoring. If we identify issues or problems, you know, we can help respond to those quickly.
Right.
Shell has never had an incident in any of their deep water fields.
Yeah.
Knock on wood, but
but
not just knock on wood.
Right.
We take a lot of steps to do that. You know, a very good
Yeah.
safety record, but it only takes one. You know, the human element's still there. We've got lots of really good equipment that protects us. But if things line up just right, you know, terrible things can happen. So you do your best to make sure that those things don't happen.
It's true that in 60 years of offshore drilling, accidents like Horizon have been extremely rare. But as we push into more challenging environments, here and around the world, the risk will increase. Future oil supply will be hard. But supply is just half the equation. What about demand? I went to see the Richmond refinery, which powers 3 million people per year.
Gasoline is about 50% of what we make, and there's many different grades of gasoline depending upon the season and where they're being sold. Jet fuel is the second largest product we have. It's about 20% of our product slate. And then diesel fuel.
So mostly fuels and certain kinds of lubricants and things like that?
Yep. We ship product over to a marketing terminal, and the trucks that will deliver right to gas stations will pick up from the marketing terminal. We'll also ship product by pipeline. It goes to the airports around here locally, or it goes throughout the state by pipeline.
Richmond makes 25% of the gasoline and nearly 70% of the jet fuel for the Bay Area. It's something like a power plant for transportation, taking the energy and oil and distributing it through gasoline.
It's not often recognized, the incredible energy that you can put into a volume with gasoline. It has 4 times the energy density of liquid hydrogen. The stuff that we put into rockets, this fuel has such enormous technical advantages that displacing it, we've seen, is not easy.
It's a miracle.
Yeah.
Think about it. You can go 350 miles on a tank of gasoline. 350 miles, a whole family in a 2-ton automobile based on a tank that's just this big.
Right.
And then there's not even any residue.
Yeah.
There's no ash. It's all gone, and you fill it up again. You can fill it up in 3 or 4 minutes. It's truly a miracle. It's very hard to replace.
The maximum size ship here at the Richmond Long Wharf is 750,000 barrels a day of product.
750,000 barrels.
Correct.
The U.S. consumes about 20 plus million barrels of oil a day.
That's correct.
So you're looking at about a 30th of the daily consumption of crude oil and gasoline on one tanker.
That's correct.
So maybe 45 minutes of what we consume in this country on that big boat. That's a lot.
Puts it into perspective, doesn't it?
That's a lot of consumption. But it's amazing how much demand there is. And that's just for the U.S. The world uses a tanker every 13 minutes. And as population and development increase, so will demand. Combine that with difficult supply, and future oil will be expensive. Around then, I was asked to speak at an energy conference in India. In many ways, India is more beautiful than I had imagined. And more exotic. And more crowded. There are people everywhere, in nearly constant motion. Vehicles at every speed, on every road, at pretty much every hour of the day or night. Millions of new drivers finding new ways to fit in too few lanes. India already makes more cars than the US, and nearly all of them running on oil.
Thank you.
It's very appropriate this meeting is in India. India will soon become the largest populated country in the world. It's growing, and the demand for energy is growing. And so many of the things that India does are going to lead the world as we move forward.
All of a sudden, you're creating a new middle class in China and India. That's hundreds of millions of people who don't yet have cars, but know what cars are and know they want them. And so as their incomes rise, their consumption of automobiles is going to rise, and that means the world's consumption of fossil fuels, particularly oil, is going to rise.
Right.
But also their demand for electricity is going to grow. One of the scariest statistics I've heard in the time I've been in this job was told to me by an Indian energy official. He said, you know, we have 600 million people in this country without access to electricity today. Can you imagine providing what the challenge is? That's 2 United States. Can you imagine providing electricity for 2 United States? And they want to do it in the next, 20 to 30 years. And they'll be adding population at the same time. So, and that's going to be coal.
In 2 or 3 decades, the energy demands of India and China are expected to exceed those of the US and all European countries combined.
In terms of the carbon emissions, the U.S. will soon be a minor player in this. Most of the carbon emissions will be coming from China, India, and the developing world. We will develop carbon sequestration, but it will be too expensive. They will not adopt it. This will become a point of friction in the future, which we will not solve. And assuming the calculations are right, we will have several degrees of global warming, which we will learn to live with because there will be no alternative. Because unless it is really cheap and affordable, the developing world cannot adopt it. And we can't afford to subsidize these huge growing nations whose economies will soon be so much larger than ours.
Coal and oil, electricity and transportation. Just as it did in the West, coal will power the development of China and India, but it will not be clean. Oil demand will increase, and so will risk, and so will price. The challenge then is not just to adopt alternatives, but to maintain the benefits of oil and coal without their disadvantages, and at a price we can all afford. can it be done? Oil makes up the largest portion of our energy use, so oil alternatives were the place to start. For 30 years, the U.S. has been the leading producer of biofuels.
Hey, Scott.
Hey.
You ready to take a ride?
You betcha. What do you got here?
Well, it's my secret. We're going to tie it on the tractor, and we're going to go out, and I'll show you what we're going to do with it.
Okay. You got me a little worried.
Yeah, let's put it on the bucket.
All right.
Now, up a little bit. There you go. All right, let's get on and we'll go. I'm going to let you
Let's
drive.
do it. Oh, good.
Yeah, I'm serious. Yeah.
We may never get there.
Crank it up.
Watch your dog. Good? How many gears does this have?
About, I don't know, 16?
Oh, good.
I think biofuels, it's the easiest thing to do because it's most similar to petroleum.
We're used to it.
And put in combustion engines, so we don't need that many changes. The United States has used corn, but the problem is you got this big, huge plant, and all you're using are those little tiny corn kernels.
So you're actually just using the food.
It doesn't make sense in many ways. You know, not only is it competing with food, which, you know, raises some moral questions, but it tends to be much more energy intensive than other ways of growing biomass. It tends to have a much larger carbon footprint, and it uses much more resources, fertilizer, and other stuff.
Okay.
So ideally, we want to move to a next generation of biomass material.
In Louisiana, they're already growing this next generation of crops. But will they be a better feedstock than corn?
Boy, this is an amazing root system.
To give an idea how tall it actually is, this is a 20-foot pole. The other day I measured, it was 18 feet.
Now, how long have these been growing?
Well, they were planted in May, middle of May.
Of which year?
This year.
May of this year?
Yeah, this is Jack and the Beanstalk territory here.
And we're in September now.
Yes.
Now, what is it? I mean, what are we looking at?
Well, it's a hybrid sorghum. It's bred especially to make cellulose.
Okay.
And the cellulose is going to be broken down into making ethanol.
If we look to the future of biofuels, we need to use better feedstocks.
Right.
We should not, in my opinion, be using a lot of food to produce fuel.
Yeah.
Right? And so we need to learn how to turn lignocellulose material, the structural material of plants, into fuel.
So the actual stalk.
The stalk, the leaves, some of the roots, and so on.
Right.
It seems cellulosic crops can be very productive on farmland and in a warm climate. But what about where conditions aren't so ideal?
New York State is not a corn-producing state. We can produce trees quite well, and we grow a lot of the perennial grasses quite well. So if you're looking for a national initiative on biofuels, you need to be looking at feedstock availability across the country, not just what we have in the Midwest or the Southeast, but how all parts of the country can play in this initiative.
Mm-hmm. Can I pull one?
Oh, yeah.
Is that all right?
Yeah.
It's pullable.
They're pretty
Oops.
tough.
Broke off.
Yeah.
Switchgrass is just one of a number of perennial grasses that we can grow in agriculture across the country. And so why not look at different possibilities?
So you're saying these kinds of grasses can be grown in places that just don't make sense for food crops?
What we typically call marginal land. And we've got no shortage of marginal land in this area, which is why you see the changes in agriculture that we've seen from a lot of small dairies over the years to a lot of land that's just sitting idle.
So far, cellulosic crops look good. High yield per acre, on marginal land, and in different climates. But what about turning them into fuel?
What we do in this laboratory is very much about microbiology, using microbes to do the conversion of sugars into biofuels.
So there's sugars in this fibrous cellulosic stuff.
Yes.
And you're trying to liberate it.
Exactly.
Okay.
Okay. The challenge, though, is how do you liberate those sugars in a very cost-effective way? Now, I can look to you dead in the eye today and tell you we can make ethanol from cellulosic material. It's a no-brainer. We know how to do that. I can't tell you for sure that we can do it economically. It's one thing for me to say I can do great things here in the laboratory with my reactors.
I've gone from this to that.
Exactly, but it's another issue to really scale this up into hundreds of thousands of gallons, millions of gallons.
Yes.
So now there are some demonstration scale facilities, you know, a few million gallons a year, 10 million, 15 million gallon a year facilities, you know, pretty, in an energy sense, very small.
Right.
You know, we're talking now, I think this year the US produced 25 million, 30 million gallons of ethanol from cellulose.
Okay.
You know, compared to 10 billion
Right.
of the corn ethanol.
If I'm hearing you right, Dan, one of the great challenges then, as with most things energy, is scale. Just the scale of taking a low-density fuel, a crop, and converting it into a high-density liquid.
You know, for bioenergy, scale is exactly the challenge, is exactly the problem. And because we use so much energy, it's mind-boggling how much energy we use. And if you make it from biomass materials, from land, you just need huge amounts of land.
Right.
I think in the end, we, the world, are going to decide that biofuels are a good option.
Okay.
But we'll never see biomass replace petroleum. It'll never happen.
Right.
If biofuels won't replace a large percentage of oil, what will? Some say compressed natural gas, or CNG.
This is natural gas, just like you burning your stove at home.
Okay.
Except we're going to run it through a compressor and pump it up to 3,800 pounds and then put it in the bus.
3,800 pounds is a lot.
Oh, yeah. But that's the only way you can get that much gas into such a small area.
So there's a big engine sitting in the back?
Yeah, yeah.
Is it different from a diesel engine?
If you look at it, you wouldn't notice the difference. It looks just like an engine.
Same thing.
Just like it.
Just a different fuel.
There you go. That's as simple as it gets, just like on the bus.
Is this the tailpipe?
That's the muffler and tailpipe.
So I'm standing right here next to the emission.
Oh, yeah.
Is that hurting me?
No, no.
What's coming out of there?
The emissions on these things are very low. As you can see, it's very clean. There's no smoke coming out.
Yeah.
So
I mean, on a diesel, we'd be seeing.
Oh, yeah. Well, you know, in the cleaner diesels, it's not as bad as the old smoke going out the tailpipe.
Yeah.
But still, this stuff, you never see it. Unless something's drastically wrong, you'll never see anything come out of these tailpipes.
I mean, we're in a room.
It isn't just a perception. It actually is very clean fuel. And when it burns, you just get carbon dioxide and water vapor, and that's pretty much it. You don't have all the smoke and particulates that you see in diesel. So it's a very clean burning energy source, and more transit systems are looking to get into it.
So looking at the whole system you've got here, and you've transitioned from fully diesel just over 20 years ago to now fully CNG.
Yes.
Compare that cost-wise and some of the pros and cons of making that change.
The actual cost of the fuel is less than diesel, and has been for the last several years. Natural gas is cheaper per mile to operate these buses than diesel. But the biggest issue is the cost of getting into it. You have to have compressors to compress the gas. So we have 5 really big compressors that are running all the time.
What happens is you have a higher capital cost, but you have lower energy costs.
Right.
So if you use the vehicle a lot, then you end up making it very attractive economically. Natural gas could be used in heavy-duty vehicles, in buses and trucks, that are fleets, and you have central stations.
So you get your compression done centrally, and you're sending them out from, like the bus station that we visit.
Like a bus station works very well.
If you took all of America's city bus fleets and made them all compressed natural gas, it wouldn't have that much of an effect. It's such a small percentage of the total diesel that's burned in America.
Really?
The city buses.
Yeah.
But a lot of trucks out there do also. Think of that. The over-the-road trucks, the city trucks, all the delivery trucks, okay? If you took all of those vehicles and converted them to compressed natural gas, which they could be because they're fleets,
Right.
you would have an impact.
Like biofuels, CNG will be a valuable supplement, but it won't replace oil. Meanwhile, demand for oil keeps growing, and a lot of people are worried we're running out. I went to see the Canadian oil sands, where plants like this could power 340,000 people per year.
Oil sands, if you could see it in the reservoir at the temperature it's at there in the depth, it's like a hockey puck. It's that hard.
So it makes it hard to get out.
It does. And where it's very shallow, it has been mined, but 80% of the oil sands needs to be recovered by thermal or steam methods. In the steam plant, we're using natural gas. Think of it as a big kettle.
So natural gas is being burned, boiling some big boilers.
And they keep feeding water in.
All right.
Keep taking steam off. So we pump steam in the injection well. You melt the oil out of the rock, and you end up with hot water and oil mixture coming back. Oil and water comes into this building where there's multi-stage separation process to take the oil from being at about 70% water.
Okay.
And when it leaves here, the oil has to be less than 0.5% water. I like to think of this as a heavy oil or oil sands facility, but we're primarily a water plant. To be good at this, you need to be good at recycling and treating and cleaning water.
Compared to the days of the large oil fields in the Middle East, yes, it is relatively expensive. It takes about $60 to $70 intermediate crude price for the oil sands to be economically competitive.
If you just consider resources that you might be able to get at for costs of less than, say, $70 a barrel, then we've got about another 4 trillion barrels of oil left in the ground to get out.
4 trillion.
4 trillion. And between now and 2030, we'll use maybe 1 trillion barrels of oil at most.
Once was a hockey puck, and after this building, it looks like this. Amazing.
Like any natural resource, how much oil there is to get out of the ground depends really on how much you're willing to pay for it.
Yeah.
And as the price of oil goes up, people are willing to go after more difficult resources.
So we're not running out. As price climbs, so will supply. It looks like the main replacement for oil will be different sources of oil. And as long as we have cars that run on it, we'll be dependent on it.
We've had these petroleum-based vehicles for 100 years, and we are starting this transition away from it. And the transition is towards electric drive vehicles, meaning vehicles that are propelled with an electric motor instead of a combustion engine. And so with hybrid vehicles, we're gradually shifting the balance between the gasoline and the electricity. We're increasing the electricity and reducing the gasoline.
You're weaning us.
We're weaning, yes, we're weaning ourselves off of oil slowly. We sometimes refer to a regular hybrid as really a gasoline-electric hybrid, meaning all of the energy comes from the gasoline. With a plug-in hybrid, now you get some of the electricity from the grid, from a plug. The way you do that is you put a bigger battery in that will hold more of the electricity, and therefore you can replace more of the gasoline. So basically what the difference is that you can run the vehicle in an all-electric mode more of the time. Electric motors are so efficient that the more you can use the electric motor, the better you are in terms of reducing energy consumption, carbon.
Why not just jump to electric?
The reason we're not going there fast is because the batteries are expensive.
Okay.
It's a big challenge today. We don't have the batteries at the appropriate cost and weight to compete with the range of our home, our personal auto, etc. But
they're just too heavy.
And expensive.
So how expensive are we talking? If I had an unlimited car budget, could I get an electric car that will do everything a gasoline car can do?
Wow. Nice design.
How many batteries do you think are in this thing? There's almost 7,000 batteries.
Me.
Almost 7,000 batteries.
And they're all the new...
Yeah, as a matter of fact, they just look like this. Types that you'd see in your laptop.
7,000.
Right now, we're talking, let's say there's a 244-mile range on these.
Is that what the range?
It's about the range.
With some
Assuming you
mix
drive
of
conservatively.
highway and
city, correct.
That's pretty.
Yeah, and then you've got the performance mode.
I'm guessing this thing isn't cheap.
You know, base price starts off at $109,000.
Okay.
And that doesn't include options.
On the other hand, we should not ignore the advantages of electrification. First of all, it's a pretty good performance vehicle. If you want torque, get a battery.
Now, the standard model is going to take you from 0 to 60 in 3.9 seconds.
3.9?
3.9 seconds. The sports model is going to take
Wear
you
your
from 0
helmet.
to 60 in 3.7 seconds. There she is in all her glory, being charged up.
You drive a Tesla, right?
I do. I do sometimes.
I mean, are we looking at the future there?
Well, I think the important thing about the Tesla and the electric vehicle front, because you know it's an expensive sports car with limited utility because it's a sports car. But the importance of the Tesla in the electric car movement is that it demonstrates one key aspect of electric car introduction, and it's a very basic aspect: fun.
Whoa! Whoa, that's fast. Woo! 0 to 60 in 3.7 seconds? No noise, no transmission, no gas stations? This car isn't just as good as a regular sports car, it is better. If I had an unlimited car budget, I'd be driving this one home.
We will see a gradual electrification, really the pace being driven by advances in battery technology more than anything else.
Okay.
But most importantly, if we're not going to get any of our transportation energy from oil, we're going to have to get it from somewhere else. And so where are you going to get the extra electricity to run all those electric cars?
Right.
When you go through the numbers, it's a non-trivial 25, 30, 40% more electricity we have to generate.
Yeah, that's a huge number.
Right.
Wow. I went to look at transportation, and it pointed me back to electricity. Where are we going to get 40% more power? Coal? Or can we successfully switch to an alternative? Iceland sits on a geologic hotspot, allowing them to get half their energy from geothermal.
Just briefly, what's going on beneath us?
So basically, we are on the seafloor. The sea level is 10 meters below us. That sea water is heated up by steam.
How hot?
200 degrees centigrade.
And it's those very hot waters that we tap and bring to the surface to create steam to feed into the geothermal power plant.
Right.
Boy, it's a natural.
It's quite simple.
What are we seeing here?
This is the actual well tub from a geothermal well. And as you can see, the pipes channel water and steam from these wells to feed the power plant. You just drill the well, you look at it for a couple of weeks, see what you get out of it, and then it just flows.
These wells feed steam to the Hellas Heady plant, which could power 90,000 people per year.
So this is the turbine.
This one
looks like a giant jet engine.
It works completely the same, but the other way around.
So where's the generator?
Generator's over there.
Okay, so this is where the electricity gets made. And it's remarkably clean.
Yeah.
Do you have any chemicals in this operation?
No, none at all.
Just the steam and the water?
Water and steam.
Unbelievable. What do I do with it?
Well, you put it on your face.
On my face. So this is natural?
This is natural, yeah. This is just silica precipitate from
You're going for the whole thing.
From the geothermal
All right.
line. Woo! It sort of goes under your top layer of the skin, I understand.
Is that right?
Yeah, sort of.
Silica is a
relieves-
good abrasive, that's for sure.
It's abrasive, yeah.
So it
Use it
exfoliates
also-
you.
Exfoliates.
I can't wait for my people who used to be my friends to see this.
The most amazing thing about the Blue Lagoon is that all the hot water in the spa, and even the white mud that it's famous for, comes straight out of the Svartsengi power plant.
I think every 75 megawatt power plant in the world should have a Blue Lagoon right next to it.
I totally agree with that.
But geothermal energy this powerful is dependent on the geology.
California has we have the geysers,
Yeah.
and Iceland runs on geothermal,
Yeah.
but those are places where the earth concentrates the geothermal energy into small locations. When you do that, it's really worth doing. But the average geothermal has a power density that's 10,000 times less than the solar energy.
So geothermal is regional, but the sun is nearly everywhere. Could solar be the answer? REC Solar is the largest residential installer in America.
People still don't know much about solar. It's changing, but it's still a relatively new technology, which really came about with having more popularity during the last 3-4 years.
How much of a homeowner's decision to install solar is based on philosophical or passion versus economics?
Most decision makers actually go for the economic reason. I would say 80%, 20% environmental reasons. Here in a neighborhood like this, you would get an incentive from the utility, and in addition, you get a federal investment tax credit.
Sure.
Typically, what a homeowner can achieve here is probably an 8 to 10 year payback.
The average solar array powers just 0.4 people per year, which means it'll take several years for the savings to offset the cost of the panels.
Is it 10 to 20 years, 30 years?
It depends on what you pay for electricity today.
Yeah, it's all relative, isn't it?
If you're, in Palo Alto in the middle of the afternoon, your photovoltaic, it's cost effective. If you were in Hawaii, where they have a very high cost of electricity, it could be cost effective today. Sure. On the other hand, if you have coal-based electricity right now, that you're paying, 4 or 5 cents a kilowatt hour, it may never be, really competitive. So there's not a simple answer, but in the right place, it's here today.
Turns out solar too is regional. It's affordable where sun, subsidies, and electric prices are high. But where we have all these things, can we turn solar panels into a solar power plant? I went down the road to the Diablo Valley College.
Basically, it's a parking lot canopy that provides shaded parking, but there's solar on the rooftops. So the solar produces about 50% of the campus's peak electrical demand.
Why in a parking lot? I mean, usually we see these panels up on a roof.
What we found is that if you can build a solar parking shade structure in a wide open parking lot that has lots of available space, you can actually drive the economics down much better than you can on the rooftops.
So how does a community college or an educational campus afford the front-end cost of something like this?
Well, most of them don't have to worry about the upfront cost. The campus would basically enter into a long-term power purchase agreement at a rate that is less than what they're buying from the local utility. So they're getting those savings from day one.
And they enter into that agreement with the utility?
No, they would enter that into with a financial institution that would actually own the asset.
Okay.
Okay, so say a bank would own the asset, and then we would design the project, build the project, do the operation and maintenance of it on behalf of the bank, which is selling the power to the campus for, say, 20 years. And that's where the savings get generated.
So that's a neat combination of partnerships that are going on there.
Yeah, it's a great example of public-private partnership to benefit the mission of a college campus.
With creative financing and in the right places, solar plants are a workable solution. But they're still limited by high price and low output. This one could power just 200 people per year. They're using a different technology to get more out of solar plants in Spain, like at Solarcar, which could power 1,200 people per year.
We have a huge field of mirrors, and they are continuously moving in order to track the sun and to concentrate solar radiation on the top of the tower. And we generate steam that we drive to the steam turbine in order to generate electricity.
the plants are larger and therefore more efficient. The footprint is smaller as well. And as you use the heat to produce energy, the plants have what we call thermal inertia. So they don't go on and off the grid when the solar resource disappears. So we can provide utilities or grids a more stable production.
When we were leaving Solarcar, we saw this beautiful image. The light beams were converging right in front of the tower.
When you don't have a very good day, it's sort of cloudy, what they do is they take out part of the solar field and they put it in what they call the waiting point in front of the receiver. People always love that. The people who are operating the plant, they don't like it because it's a sign that they are not able to produce as much as they could.
At 16,000 people per year, Andasol uses hundreds of mirrored troughs to turn heat into power.
Oh, that's very warm. I can feel it here.
Yeah.
It's like, woo, it's hot. Right here?
You can...
Yeah. Ooh.
The heat makes steam to turn a generator or is stored in tanks of molten salt to be used later in the day. So you're storing heat, not electrons, with concentrated solar.
Yeah. Storing electricity today is not efficient. There are no known technologies cheap enough, let's say, while storing heat is something used in other industries.
But on the day I was there, the troughs never swung upward to gather heat. This plant also never got out of the holding position.
For the large utility scale solar thermal plants, you know, they have to be in places that have very clear, direct sunshine, not kind of, you know, reflected stuff, which you can get away with more easily with photovoltaics.
Obviously, there's a big room for improvement, and we just got started. Technologies are very young. You are seeing technologies for which there are, in the case of a tower, 2 towers worldwide. In the case of troughs, a bunch of them worldwide. So there's a huge path that we will go through in order to reduce the cost of these technologies and improve efficiency.
As promising as this technology appears, it's probably decades away from being an affordable solution. We'll need some other alternative to provide large-scale power. For 40 years, Denmark has led the world in wind, which now makes up 20% of their electricity.
Welcome to turbine number 4. Coming in. So what I'm going to do now is to press the stop button. You can have the responsibility.
Absolutely. Stopping the turbine. Oh, I can hear it. It just grinds down very quickly.
Yeah.
Just a few seconds.
Let's climb to the top.
How high are we going?
It's 50 meters.
How narrow do we get at the top?
Oh, like 1.5 meters.
Okay. All right.
Okay. One important thing is use your legs.
The benefits of wind are many. It produces a lot of power.
Right.
It's fast to install and scalable in size. It does not produce CO2 while producing power. To Denmark, it's also a big export commodity. So for us, there's some additional benefits.
Sure.
In Denmark, we sort of invented the modern turbine. It was built by a combination of hardworking entrepreneurs and some visionary politicians who could see this already in the beginning, 20, 30 years ago. And of course, the consumers, me, and at that time my parents, I guess, they had to pay the price for wind energy.
Right.
So for a while, you could say we were, other things being equal, paying more than we could have done, but to build up this industry and to make sure that in the future, Denmark would reduce its dependency on imported energy.
We went from 0% of wind penetration to 20% or 22% as we're approaching now. Slowly but surely. It has been a long but concerted effort. Every year, one bit at a time.
Whoa. Woo.
like the view?
Awesome.
It's a well-known Danish concept for wind turbines.
Right.
Which is just to use standard, simple components, almost taken from the shelf.
Sure.
It takes care of itself. This fellow works for 20 years or more.
Very reliable. Pretty simple
reliable.
components.
Very simple, yeah. Keep it simple.
The three-blade turbine we see around the world was pioneered and perfected here. They can be built in months and rolled out in any number. But the turbine is only part of the equation. The rest is the wind.
And of course, when the wind does not blow, we generate nothing. That we guarantee.
One of the problems with wind is its intermittency. The wind doesn't blow all the time, and so you don't get the electricity from wind all the time. And again, because it's hard to store electricity, you need to figure out how to handle that intermittency.
The main idea is a combination of different technologies, diversification. That's what we have done in Denmark. We have our combined heat and power plants that are stable baseload, and then we have our strong interconnectors to the other countries.
Okay.
That's crucial. You cannot do this without being able to exchange large amounts of electricity across borders.
Exactly.
Denmark has made this intermittent resource a success. But this is a country of only 5 million people. All their turbines combined would power just 340,000 people per year. Can we do the same thing in a much larger country?
But this sort of shows you in Texas what's going on, so you get a relative sense of where you are.
Yeah.
Which means as soon as you take off, you're flying over 25% of U.S. wind energy capacity is here. Basically, half of U.S. wind is probably within 500 miles of here.
Let's do it.
I'm ready.
We've got almost 100,000 acres in the Roscoe Wind Farm.
100,000 acres.
And about 400 landowners. And this amazing wind resource that we've got through here.
Did you ever think you'd be using the word amazing wind?
We've cussed this wind all our life. It destroys our crops. We have sandstorms. It blows our soil away. And you talk about an attitude adjustment. Now we've had it 180-degree attitude adjustment relating to the wind. It's just been phenomenal.
You really led this thing in many ways, and I know you're a modest person, but 4 or 5 years ago, if I was standing right here with you, we'd be looking at farmland and ranch land.
The more I learned about the wind industry, the more I believed that we had the combination that we needed to build a wind farm here. It just, somebody just needed to do it.
And this is a community that's welcoming this with open arms.
Yes.
Nobody's saying, hey, not here in my backyard, not on my farm.
No, West Texas is an agriculturally depressed area. It's just an economically depressed area.
Yeah.
And we've just had to sit here and take what Mother Nature brings to us in the way of rainfall and try to make a living on this country. And it's gotten so tough that our young people don't come back. But now, with our windmills and our opportunities here that it's bringing, it's turned our communities around. We've got, for the first time ever, these landlords have an opportunity to receive a regular paycheck.
For the farmers around Sweetwater, wind turbines are a beautiful thing, and I would tend to agree. But to get 20% of U.S. electricity from wind would require another 200,000 of them. We could do that, but people may not want to look at that many turbines.
Wind power is best in windy areas, but people don't tend to live there. And so we need to get the electrical grid out to the wind farms in order to be able to bring that electricity into the cities.
We found the best wind areas, and then we came up with a plan to build transmission out to those areas and deliver it back in to Dallas, Fort Worth, Austin, San Antonio, and Houston.
Okay.
That plan is 2,300 miles of high-capacity transmission. It's about $5 billion, and we're going to have it completed by the end of 2013.
What would it take to do that nationally? Just scale it up for me a little bit.
Well, there are two debates on this.
Okay.
One is who pays for it. So would we encourage at the federal level a payment system like we have today, which is everybody pays, which is different from the way the rest of the country does. And then there's the siting issue. Nobody wants to have transmission lines running through their 100-year-old family ranch.
Right.
It's never been the case. This is going to be the challenge if the federal government says, okay, we're going to do that. We're going to site these lines. Are they really willing to get down and go property by property with county judges, county commissioners, and landowners in siting these lines? Because that's what's required.
Right.
So to make wind work on a grand scale, we'll first need to figure out transmission, and then how to manage that much intermittent power. I went to visit ERCOT, where they've been doing exactly that.
This building is natural disaster proof. This is designed to handle an F5 tornado, which is the biggest tornado we anticipate. You know, we're unique in that we have enough diesel generators to actually supply all the power we need 24 hours a day indefinitely. 22 million people that were relying on our power, we can't have little things like that happen.
Right. That your grid?
Yes, this is a graphical representation of our grid, and the different lines are the different voltages that we have in the system. But if you look at a power plant, you can see the power flowing out on the different lines.
The amazing thing about electricity is it's generated at exactly the same pace that we use it. Like,
Yeah.
isn't that a miracle?
Yeah.
I mean, what other thing, you know, exactly where supply meets demand?
We take it for granted. We flip a switch, light comes on, but actually somebody is in very short time intervals, so-called dispatching different plants, gas plants, nuclear plants, coal plants, wind plants, to match the instantaneous demand.
So I've got Houston, San Antonio, Austin, Dallas, Fort
That's
Worth.
right. That's right. And then the wind, our wind is out here in the west, and these are some of those big lines that we're moving out there to connect to the West Texas wind. If you look at this chart here, this is how we actually use electricity. And you can see that at 3 o'clock in the morning is our minimum usage, and then all day long it increases up to about 5 o'clock where it peaks out, which is mainly your air conditioning load, and then it repeats itself day after day.
Okay.
And now let's take a look at wind. The wind output does not match the actual energy usage. So because of this intermittent resource, when the demand is going up but the wind is going down, that causes us to bring on additional conventional generation that can make up the difference between the actual renewables output and what our demand is.
Gotcha. Wind is intermittent.
Yeah.
Solar is intermittent. So when they're going, they're great, but you need something you can bring up quickly to fill in that gap.
Very quickly.
Quickly.
Because, you know, we're hearing stories, particularly in these markets like Texas, where wind is a big part, that, I mean, sometimes the wind will go from several thousand megawatts to zero in less than a minute.
Okay.
And gas plants can come on within the minute, but there are many types of gas plants that can come on within 10 minutes. So the key is to encourage people to build natural gas plants that work in concert with wind and solar, and natural gas can fill in that gap.
So natural gas can support a growing amount of renewables. And a technique called hydrofracking has unlocked a huge unconventional supply in places like the Barnett Shale, a field that can power 18 million people per year.
These are gases that do not flow easily out of the rocks and sometimes have to be induced to come out, for example, by fracturing the rock through this hydrofracturing process and long horizontal drilling. Hydraulic fracturing is a way of first drilling a well and then pumping down fluids, water, other chemicals, and inducing the rock to break. And when the rock breaks, it opens up new surface area from which the gas can flow out.
Now in the United States, I think there's about 2,000 trillion cubic feet of gas.
2,000 trillion.
Yes, which would be 2 quadrillion cubic feet of gas, which is enormous. Or said another way, it's about 100 years of supply at present consumption standards. And to imagine that you never have to make any other discoveries and you've got 100 years of any resource is just extraordinary.
It's inexpensive. There's so much of it that the cost is not expected to go up in the next few decades.
Right.
The problem with it is it's a fossil fuel, and so it does produce carbon dioxide, but only half as much as coal.
But there's a controversy surrounding fracturing that centers on water.
Now, how much water are you putting in to a typical job?
You know, an average might be about 3 million gallons.
3 million gallons for the whole job?
For the whole job for the whole well.
Gotcha. And how many wells are out here on this pad?
On this pad, we have 5 wells.
Okay. So you do each one of those with 3 million gallons. It's a lot of water.
It's a lot of water.
You know, you pick up the paper today, you look on the news, and there's people talking about fracturing. They're looking at it in Washington. You put other chemicals and kinds of things in it.
There's some additives. Pumping the water down itself, there's quite a bit of friction, so we add a little bit of gel to it to slick it up.
Okay.
It makes it smoother.
Okay.
We put in some corrosion inhibitor, you know, chemicals like that help us, but over 99.5% of the fluid that goes in is just water and sand.
That does mean that there are 15,000 gallons of additives going into each of these wells. And what people are worried about is, will fracturing contaminate our water supply? I went to see the agency that regulates fracking in Texas.
We have overseen the process of hydraulic fracturing for decades now. And we're not aware of one documented case of groundwater contamination, for example, which is the big concern that is voiced federally and in Congress.
In all the fracturing that's been done in Texas so far?
Those wells up in the Barnett, you drill down about 8,000 feet. So there are over 1.5 miles of shales and sandstones that protect the groundwater, the near surface groundwater, from contamination.
There have been a number of confirmed instances, as well as some number of alleged but unconfirmed instances, where natural gas drilling has negatively impacted groundwater supplies. But to the best of my knowledge, none of those confirmed examples were related to a hydraulic fracturing operation. And in fact, most of the risks occur at the surface rather than downhole.
Right. So the hydrofracking down here, if I understand you right, you don't know of any cases where the actual hydrofrac process caused problems at the surface, but it's things related to the hydrofracking that are done at the surface that could cause issues if they're not done properly.
We can have fluids that are spilled at the surface. Waste can be spilled as they leave a lease. Pits for the temporary storage of fluids and waste can leak. Hydraulic fracturing potentially is a problem, but in my mind, it's one of the least risky aspects of a natural gas operation.
Right.
The Congress is moving towards requiring more supervision over these fracturing processes. It is certainly, I would say, not clear to me today that there have been major consequences, but I think this is an area where what we need is good, objective measurements, analysis, and then whatever measures are required for environmental protection will be taken.
There are certainly many other deposits of shale gas and tight gas that other countries can access. Look, natural gas is much cleaner than coal, and I think this technology is becoming a real game changer and as we think about a low-carbon energy future.
It seems the risk is not so much with fracking, but with handling the wastewater. Hopefully, gas producers and regulators can resolve these issues so we can have access to this abundant resource. In other parts of the world, conventional natural gas supplies are growing too.
How far off the shore are we? You see that platform up there? Way up there in the distance on the horizon? Yes, sir.
Yeah, that's an Iranian platform. We're right on the border here, and this is where all the ships line up to get out the straits.
Gas, there's a tremendous amount of gas. The problem is that because it's a gas, if it's not close to the people who want to use it, it tends to be expensive to move it.
The gas is piped into Ras Laffan, processed and made into LNG, and then shipped all over the world.
In LNG, we turn the natural gas, we freeze it basically, so that it turns into a liquid, and then we can put it in a ship and move it across the ocean.
Qatar was sitting on this resource, which is the North Field for many years, was discovered in 1976. So there was a vision in Qatar, why couldn't we make this natural gas economical? I mean, Qatar in the last 10 years has, grown from zero production to about 30% of the world market. And the only way we can make it economical is that we build very large-scale plants.
This one plant is so large, it could power 18.5 million people per year.
On the shipping side, now we're building what we call the QMAX ships, and the QMAX is 250,000 meters.
250,000 cubic meters on one ship.
On one ship.
So this is gigantic.
Gigantic.
So the ship is being loaded now, and then you have water falling down the side of the ship.
Yeah. We call the water curtain. This protects the ship's hull from any spills because, as you know, this liquid is minus 163 degrees Celsius, and if it touches the hull directly, it will make the hull crack.
How do you keep the LNG cool once it's loaded?
They have a very huge insulation boxes which can keep the temperature inside the tank steady.
So this is a giant thermos.
Yes,
a giant cooler. It never loses heat.
Yes.
Unbelievable.
We consider this as a pipeline in the sea. I mean, these ships,
exactly,
they are as good as a pipeline. In fact, they are more reliable. They don't have to go through the geopolitics, where crossing countries and the problems, some of the issues which we have seen, last years. I mean, it's very secure supply. Yeah.
We may even eventually see essentially a world market in natural gas develop as it has for oil, and that would give a lot more diversity of supply.
Low carbon, low price, and the ability to back up wind and solar mean that natural gas will likely be a vital part of our energy transition. But there's one more huge energy source that I hadn't looked into yet: nuclear. This plant could power 1 million people per year.
You can see the barriers here. Now you're going right along the protected area of the plant. But quite a bit of concrete measures that were taken after 9/11.
But since Fukushima, people are worried that nuclear isn't safe. Comanche Peak is just 150 miles from my house, and I needed to get a better look.
Exactly.
So we're getting a peek inside here.
You can, and that's where the equipment all comes in. And one of the things that's nice about this view is that you can see the thickness of the concrete, of the walls for containment. And what you don't see there is the rebar, and it's rebar throughout that concrete going all the way up. It's
we're not talking rebar.
No,
we're
rebar,
talking
it's 2.5 inch rebar, thickness. Arm. That's correct. Basically like your arm.
What happens if something flies into a structure like that?
Well, there would be damage to the outside structure, of course. The equipment inside would be protected.
We're in tornado country.
Absolutely.
What happens?
And these structures are designed for the worst case tornadoes. We're talking about 300 mile an hour hitting directly at this equipment. Structure would be protected.
300 mile an hour.
300 mile an hour, yes. Scott, we just entered the radiation controlled area.
Yeah.
And one of the things you were given was a dosimeter to measure your radiation. What you'll note is that it's reading 0.0 millirem.
Okay.
And it'll continue to monitor you throughout your stay in here.
Gotcha.
So, for example, I've been working in the nuclear industry for 28 years, and I've picked up probably in the neighborhood of 200 to 300 millirem. throughout the 28 years. So
The whole time?
The whole time, yes.
And that, you said, was a normal background for a year for a person?
For a year for a person, that's correct.
These are huge generators.
Absolutely. There's 4 of them, 2 per unit. So you only need 1 during an emergency. But again, from a redundancy standpoint, we have a backup.
Running on diesel.
They run on diesel fuel oil. The tank is located underground, a little different than what Fukushima had. And we also have a day tank of fuel oil that's located above, above the diesel.
And one of these generators could run the critical equipment.
It would run all the equipment necessary to keep protecting that core and that fuel.
So they're not running now.
No.
What are we hearing?
Ventilation. Ventilation system. You'd know when it's running.
Yeah.
What you see here is the Unit 2 spent fuel pool. You see Unit 2 containment. That's a containment
Yeah.
for 4.5 foot thick concrete with rebar. It's all located there.
So you remove these spent fuel rods underwater.
Correct.
Water keeps it cool.
That's correct.
So I'm wanting to check my
Check your dosimeter. It would be the right thing to do.
my rims here, and let's see. 0.0.
That's correct. That's what I would expect.
That's less than I would get if I'd been outside all day.
You could stand here for the next hour and be reading 0.0. Yes.
The dangers of nuclear power, although they're real, are less than the dangers of not having sufficient energy with all the problems that brings. They're less than the dangers of coal. They're looking desperately for natural gas, but all fossil fuels produce carbon dioxide, and the world is seriously worried about increasing even further the carbon dioxide in the atmosphere. So everything has its dangers, and as we begin to appreciate that, we realize that nuclear looks better.
Yeah.
But there are other things, getting the nuclear reactor to be less expensive. A nuclear reactor, unlike a coal plant, the fuel doesn't cost much.
Right.
I mentioned 1/10 of a cent
Right.
to get a kilowatt hour. The expense is up front.
You know, when you build a nuclear plant, you need to put down, say, $5 or $6 billion just to build the plant and get it running.
For how big of a facility?
Say for a 1 gigawatt electrical plant, about $6 billion. So you have to put down all that money out front, and then you're relying on the revenue stream from the electricity you generate over the next 30 or 40 years in order to become economically profitable. But if you look at technologies to generate electricity that can operate at scale, that have low emissions, and are available now, not 20 or 30 years from now, nuclear comes up awfully high on the list. In fact, it's very hard to see how the world is going to meet its emissions goals without a significant fraction of nuclear energy.
So what would a system with more nuclear energy look like?
Since France has no coal, no oil, they decided that there are no other solution that go full nuclear. So nuclear energy was born out of necessity, period. And so in about 25 years, France went from almost no nuclear energy to now about 80% of electricity is made out of nuclear energy. The safety record of the French nuclear system has been impeccable. France has the cheapest price of electricity in Europe. And the CO2 footprint of France is minimal now. So the advantages are tremendous. And one of the reasons actually there is so much acceptance in France about nuclear energy is because we can tell the public that we have a solution for waste management.
Their solution is recycling, which they do at Le Hague, a plant that could power 17 million people per year. Here, spent fuel from France, Japan, Germany, and other countries is reprocessed into new fuel.
And you can see now the first step of the process, the fuel rods moving out the cask.
He's lifting the whole...
Yes, very slowly. Very slowly, and you can see it on this control screen.
How many of those do you do every day?
It's 1 cask per day.
1 cask per day.
Yes. One of these fuel assembly is producing electricity for 25,000 people. Inside, you have 96% of the material that we can reuse to produce a new fuel. This is very interesting.
So 96% of the fuel is reusable. Why isn't that being done all over the
Because
world?
they have fresh uranium, reserve of fresh uranium. But lots of countries are interested by recycling now because, of course, we can reduce the volume of waste and because we can have a reserve of energy. And we know now that we will have in the futures problem with the reserve of energy in general.
So this is a giant swimming pool.
Yes.
But you don't swim. And how deep is the water?
The depth of the water is around 10 meters.
10 meters?
Yes.
And it acts as a big cooling system. I'm looking at basket after basket after basket. How many baskets are stored here?
We have 19,000 fuel assemblies stored here at the Lag plant.
19,000?
Yes.
That's a uranium mine.
Yes, it's something like that. It represents 6 months of oil production of Saudi Arabia.
This facility,
yes,
the
it's
uranium
really big,
here
yes.
represents the equivalent of 6 months oil production
Sure.
in Saudi
yes,
Arabia.
exactly. It's a real reserve of energy. In the used fuel, you have 95% of the uranium, 1% of plutonium, and 4% only of fission products, which are the final waste. So we vitrify them, put in containers, and in this interim storage. Each French people is producing 5 grams of fission products, vitrified waste, per year. So this is the equivalency of 20 cents euro coins.
So that's the fission waste for one person for 1 year.
Yes. In this room, we have 400 pits.
400?
400 pits. And we have 3 rooms like that.
1,200 holes, and 2 is 1 million people. Yeah. So you're looking at 600 million people of waste equivalent.
Yeah.
600 million people in 3 rooms this size. So it's a very elegant solution to recycle and reuse the uranium and the plutonium.
Yes.
And just separate out those few things that are not usable.
Even more than zero emissions, it's this astonishing concentration of energy, far greater than any other power source, that's nuclear's biggest benefit. But that's also why it must be handled with care. So what have I learned after 2 years in the field? That the switch needs to happen first in the way we understand and use energy.
If we look at today, the foundational energies, the energies that built our modern economy, are oil, transportation, and coal, electricity. What the plot shows is the higher the price goes, there's more oil. The reserve is dependent on price. There's another 7 to 8 trillion barrels of oil out there at the right price, or oil equivalents. So let's look at the alternatives. What are our options to oil and coal, these foundational energies? If we go back to our graph now, we've looked at solar, wind, geothermal. They're putting solar panels as coverings to parking lots. It's hot, and there are no trees, let's use it. For alternatives, scale is the big one. Getting enough volume to begin to make a substantive replacement. How about hydro? Norway is phenomenal. Turbines under the mountain, you don't even know they're there. The water accelerates down the hill, flows out into the top of a fjord, it's perfect. Beautiful, clean energy, and if we all had topography like Norway and renewable rainfall, we'd be finished. So you're getting the picture here that nothing's perfect. No energy source is without some challenges. So what does this mean for our energy future? You can see oil. It was 50% just 30 years ago, and it's down to 34% today. Coal, 29% today. Natural gas, 23% and climbing. Nuclear, 5% and climbing.
hydro 6% and declining, and the renewables, biomass, biofuels, geothermal, wind and solar combined, around 2% today, and will rise substantially out into the future. But it still doesn't tell us about the transition. Where does that start to happen? If we combine our foundational fuels, oil and coal, those move up and slowly decline in the future. If you combine renewables with hydro, you see that they move up, but not enough to be primary sources. The intermittency challenge is too great, and until that's solved, there'll be great regional supplements. And finally, if we combine nuclear and natural gas, they sit in the middle today and are growing out into the future and approaching the foundational energies. But we still don't see that crossover point until we combine nuclear and natural gas with the renewables. And now we see, some 50 years out, the crossover between foundational energies and energies of the future. It's not going to be easy. Natural gas will nearly have to double, and it can. Nuclear reactors will have to build nearly 3 times as many as exist today. And renewables go up 5-fold. Can we be certain that we can meet this challenge, and how can we do that? Well, the easiest way, the best way, is the energy that we don't use. That will reduce these multiples. Natural gas, nuclear, renewables will go down. It would mean 200 fewer nuclear reactors. It would mean 100,000 less wind turbines. We could meet that 50-year crossover with less infrastructure required. As I've traveled the world, I've come to realize that, in fact, there's a tremendous role that each of us plays in efficiency, in changing our energy behavior. What you do and what I do are the most important part of our energy future. You remember how I added up my energy use? Well, I decided to subtract from it.
We're going to spray the radiant barrier on your decking.
Oh, okay. Because that's where all the heat's coming in,
right.
The dark shingles.
Exactly.
The world uses, 40% of its energy in buildings. You can insulate your house. That's got a short payback time and reaps great energy benefits. Put in a better hot water heater, for example. Check the windows, the leaks in the doors, and so on. These are relatively simple and largely cost-effective things that the individual consumer can
And no matter?
And they do make a difference at the individual level. Of course, if everybody does them, they will have an impact at scale.
Hey, how you doing?
Finished product.
Looks a little different from what we had before, that's for sure. How's it going out here?
Great. Pretty close. A few more hinges, we'll be ready to go.
Have a lot of lights. You can see that little curly Q one inside.
You ready?
Ah, here they come. We got on board at the Bureau, too, with our own solar parking canopy. Now, these things may not be for everyone, but they don't have to be. The important thing is to change the way we think about energy, so we can change the way we use it.
Just by doing a whole lot of simple things, mostly paying attention, turning things off when we didn't really use them, I was able to reduce the electricity use at our house by almost 40%. Each of us could live just as comfortable lives, but use less energy.
It directly correlates. It's a really simple relationship. Yeah. Use less, emit less.
Yeah. These are steps that save money, they save energy, they save emissions, they're good for the climate, they're good for security, they're good for your pocketbook. That's the place to start.
So any way you slice it, energy efficiency is good, and that's what we recommend any government focus on first. And letting a democratic society make its choices based on the information available to it. And I'm confident that the citizens in our countries and the citizens in countries like China and India will make the right choices if they have the right information.
Energy powers our lives. We are the end users, and that gives us a remarkable amount of control. We just need to do something about it in a way that makes sense for each of us. So when I found out our neighborhood allowed golf carts, we got one for errands and taking the kids to school. And it's powered by a battery. It's certainly not a Tesla, but it's a good start.